Today, we'll be talking about some definitions in the Riemann sums. We want to look at how to describe or define the partition of an interval, the norm or mesh of an interval or of a partition, and what we call the tagged partition. Remember, we have said that the Riemann sum, which we can denote as S, is used to approximate the area under a given curve. The Riemann sum is used to approximate the area under the given curve. Let y equals f of x be a continuous and non-negative function. A continuous and non-negative function, that is, f of x is greater than 0. Defined on a closed interval AB as shown. For example, that is our x-axis, that is our interval A, and that is the interval B. We use the Riemann sum to estimate, to approximate the area bounded by our curve f of x and the interval AB. The area bounded by the curve f of x and the interval AB. To do this, if this is our curve again, that's our x-axis, that is our y, that is the curve f of x, spanning from the bound A to B. It means that we are going to divide this area under the curve. We are going to partition it into sub-intervals. We are going to divide or partition it into sub-intervals spanning from A, which is equal to x of 0, to B, which is equal to x of n. That now takes us to the first definition which we want to discuss today, which we call the partition of an interval. The partition of an interval. The partition of an interval. That means we divide our interval AB into n subintervals such that it spans from A equals to x of 0 to x of 1, x of 2, down to x of I minus 1, x of I, and then down to x of n minus 1 to our B, which is x of n. That tells us that our A, which is equal to x of 0, is less than the x of 1, less than x of 2, and that is less than x of I minus 1, which is also less than x of I, and that is also less than x of n minus 1, which is less than x of n, which is our B. So what are the sub-intervals that we can bring out from here? Our sub-intervals are x0, x1, x1, x2, down to x of I minus 1, x of I, and then down to x of n minus 1, x of n. These are the subintervals. These are the subintervals. These are the subintervals. Therefore, the partition of an interval, how do we describe it now? The partition of an interval is a collection or a finite ordered set P. Set P of what? Of all the subintervals. Finite ordered set P of all the subintervals. I1, I2, down to I sub I, down to In. Of non-overlapping closed subintervals whose union is the interval AB. Therefore, the partition P of an interval is denoted as P equals to xi minus 1 to xi, the interval, the set of the subintervals from I equals 1 to n. That is the partition P of an interval. We are moving on from there. What then? How do we get the width of these subintervals? How do we get the width of these subintervals? Remember that we have said that our subintervals are what? X sub 0, x of 1, down to x of I minus 1, x of I, down to x of n minus 1, x of n. All these, the union of all these, give us the interval A to B. The union, the width rather, the width of each subintervals denoted as H or delta X is given as what? Delta X equals to Xi minus Xi minus 1. That is the width of each of the subintervals. The width of each of the subintervals. And that takes us to the next thing we want to try to define or describe. in this video, and that is the norm or the mesh of a partition. The norm or mesh of a partition. The norm or mesh of a partition is the width or the length of the largest subinterval. The width or length of the largest subinterval. It is denoted as that. Therefore, our norm or mesh of partition P is the maximum. Remember, we said the width of the largest subintervals. That means the maximum of each of these. The maximum of what? Our delta x1, delta x2, down to delta xn. And that is still the same thing as the maximum of xi minus xi minus 1 from I equals 1 to n. The maximum of that gives us the mesh or the norm of the partition. The norm of the partition. Now, if in each subinterval we select a point, if in each subintervals we select a point, as we normally do, if we want to estimate the area under the curve, you might select the left hand point or the right hand point or the midpoint of the subintervals. Those points selected is called the tag or the sample point of the interval. For example, if a point Ti is selected in each subinterval such that Ti is an element of each subintervals, xi minus 1 xi for I from 1 to n, then the point Ti or T sub I is called the tags or the sample points on the subintervals. The tags or the sample points on the subintervals. And so this takes us to the third definition which I want to look at, which is the tagged partition. Tagged partition. A tagged partition is a set of ordered pair of the subinterval and corresponding tags. it is denoted as P star or P with the overhead dot. And our P star is equal to what? Remember we said is a set of ordered pair of our subinterval and the corresponding tag, where what? Our Ti is the element of I, for I ranging from 1 to n. And it is still the same thing as what? We can express our subinterval as xi minus 1 to xi with our tag I from I equals 1 to n. Those are the three definitions which I'll be looking at in this video. In the next video, we'll be looking at how to estimate the area under the curve. I'll be taking some examples.